Have you ever wondered how electronic circuits can selectively amplify certain frequencies while rejecting others, or how a radio receiver tunes into a specific station? This remarkable ability often relies on a phenomenon called resonance, a critical concept in alternating current circuit analysis. For a parallel resonant circuit composed of an inductor and a capacitor connected in parallel, the resonant frequency, often denoted as F subscript R, is calculated using the formula 1 divided by 2 pi times the square root of LC here. L represents the inductance in henries and C represents the capacitance in farads. This formula pinpoints the specific frequency at which the inductive and capacitive reactances perfectly cancel each other out, leading to maximum impedance. The core mechanism behind this formula lies in the energy storage properties of inductors and capacitors. At resonance, the energy oscillates between the magnetic field of the inductor and the electric field of the capacitor. The inductive reactance, which is 2 pi FL, exactly equals the capacitive reactance, which is 1 divided by 2 pi FC. When these two reactances are equal in magnitude but opposite in phase, they effectively cancel each other out from the perspective of the power source. This cancellation results in the total impedance of the parallel LC combination becoming theoretically infinite for an ideal circuit. To apply this formula, first ensure your inductance L is in henries and your capacitance C is in farads. If they are in millihenries, microfarads, or nanofarads, remember to convert them to their base units before plugging them into the equation. For instance, a 100 microfarad capacitor becomes 100 times 10 to the negative 6 farads. Once converted, simply multiply L by C, take the square root of that product, then multiply by 2 pi, and finally, divide 1 by that entire result. Understanding parallel resonance is key to designing frequency-selective filters and oscillators. A fascinating aspect is that while the parallel combination presents a very high impedance to the source at resonance, there is a large circulating current flowing between the inductor and capacitor, which can be much greater than the current drawn from the source. This circulating current is often quantified by the quality factor, or Q factor, of the circuit. Mastering the parallel resonant frequency formula empowers you to accurately predict circuit behavior, enabling precise frequency tuning and filtering in numerous electrical engineering applications. It is a foundational concept for anyone working with alternating current systems, providing a critical tool for both analysis and design.